basically, ORB is another kind of feature detector, but one thing it offers is that it is patent-free, and it has some other performance benefits. So it's based on a binary descriptor called brief. This particular feature is rotation invariant and resistant to noise. And you can use this for basically object detection or 3D reconstruction. Now CIF and SURF descriptors will still give the best overall results when detecting specifically patterns in video. Now, for the ORB algorithm, this algorithm has been shown to basically provide a very well-performing feature detector that performs consistently. And the main benefit is that it can be significantly faster than algorithms such as CIF because it is less computationally expensive. So stereo vision, OpenCV also has a number of algorithms. So here we have three distinct stereo matching algorithms. VM is known as block matching, where basically we take two image pairs and we apply a back block matching algorithm between the two. And the goal of it is to basically, figure out what is the stereo disparity and also extract depth from these two images. BP is known as belief propagation. What it does is it calculates the marginal distribution of each unobserved node, conditional on any observed nodes. Belief propagation is commonly used in artificial intelligence and information theory. Another one is CSBP, which is constant space belief propagation. It's similar to BP, but basically by fixing the number of disparity levels on the original resolution, this method allows you to solve the message updating problem in a time linear in the number of pixels contained in the image, and requires only constant linear space. So if we look over here by these images, I mean, the ideal result you would like to see is this stereo disparity with as little noise as possible. So if we look at CSBP, I mean, you effectively see like smooth shades of gray, where basically is able to detect, the depth from these two images, and it does so. If you compare it with the block matching, it's significantly noisier than. So CSBP is going to give you better results. So one thing to note about OpenCV is that if you look at the GPU versions and the CPU versions, you can see that they're not going to give you the exact results. But this is known, and basically the algorithm is designed such that it is able to handle these discrepancies in the results. I mean, what typically happens is that based on a serial and a parallel algorithm implementation, you're going to get differences in maybe the least significant bits, and also OpenCV basically designs a lot of these algorithms to handle these differences. So Viola-Jones is one of the first object detection frameworks that actually provided object detection rates that were close to real time. So what's nice about this Viola-Jones is that you can train them to detect different things. And one of the first things that they did is they basically trained a targeted set of 4 faces. And basically, feature detection involves taking sums of image pixels within a rectangular image, and by evaluating this rectangular image with a strong set of classifiers, basically you can if you take, let's say, hundreds of thousands of photos, you can basically train these classifiers that what is and what is not a face. So the nice thing about having these classifiers is it allows you to basically arrange them in cascade order of complexity. So by basically going through kind of like a decision tree with these classifiers, you can quickly identify what is and what is not a face. Generally, for this particular algorithm, if you're running this and there are no faces in the screen in the video, it will generally take the longest to detect. But if there's a face there and it basically picks it up, it doesn't take as much computational time for that. So optical flow is one of those algorithms that basically the goal of it is to basically calculate two displacement fields or vector fields between two images. So this is typically used for estimating images, motion within images. And there's a number of applications for it. So we can look at one which was recently added to OpenCV 2.4, Brock's optical flow. This is actually a very high accuracy optical flow estimation based on the theory of warping. And basically, one of the benefits of this is it's extremely accurate and it has very few angular errors compared to other optical flow estimators. It is a lot more computationally expensive, but if you're dealing with things like optical flow for film or for very high precision vectors, Brock's optical flow is going to give you the much more accurate results. Pyramid Lucas Canard is also a widely used differential model, and basically it assumes that the flow is constant in a local neighborhood of a pixel, and it basically solves the equations for the pixel by using the least squares criterion. By combining the information from nearby pixels, the Lucas-Canard method can often resolve the inherent ambiguity of the optical flow equation. This optical flow method is also less sensitive to image noise than pointwise methods. Okay. And for some of these algorithms, we achieve a speed of 6x. So you can use optical flow for things like image stabilization, feature tracking, or even video encoding. All right, so this is a little video of what it looks like when you have optical flow running. So the video on the frame on top, what you see a lot of these little blobs that represent the it's basically computation of the dense optical flow for a particular video. So the color in this scene represents the direction of the moving pixels. And the intensity of the color is also represents the speed. So if you see a more distinct color, stronger color, that means that you have a particular object within the scene that is moving at a higher velocity. So if you want to get started with OpenCV with GPU support, you can get the packages from this web link on the Willow Garage site. You'll need a CUDA-capable GPU and also the NVIDIA GPU Toolkit if you would like to build this. So what does it look like if you're developing a program? Basically, for OpenCV GPU, it has specific data structures which are used for storing image data within GPU memory. And basically, we defined an explicit class for this that basically keeps track of all of the memory objects with reference counts. We also have some specific data structures to define that whether these objects are in CUDA memory and whether they support pin memory. So pin memory is basically fast system memory that is available for transferring data to and from the GPU. We basically use pin system memory because we don't always want to have the CPU involved to do memory copies. By providing this API with a pin memory surface, you can basically allow the GPU to basically kick off DMA transfers without any CPU intervention needed. And also we added, for OpenCV, we added a class to handle streams. So streams is basically a way for, to describe an order of operations on the GPU. And what this allows you to do is, if you have streams, you can define, okay, what is the data dependency? So allows you to basically specify how to overlap your data transfers with your compute. So you can basically run something in OpenCV in a streaming fashion, especially if you're capturing live video. You don't necessarily want to be stopped, you don't necessarily want to stop computing just to transfer a piece of data. I mean, we can always kick that off in a separate stream, and we can transfer data in parallel while we're doing running an OpenCV kernel. So this is what the code looks like. On the left side in blue, this is basically describing or instantiating a HOD descriptor. And this is, on the right side, this is what you need to have the GPU version. So basically, we define specific interfaces that look just like the CPU versions. We basically just add a GPU there. And then for data structures like the GPU frame, we make sure we specify that this is a GPU frame. Of course, we have to explicitly handle some of the data transfers, but this allows us to optimize it in a way that we can specify we want overlap with compute. And so for the most part, the function interfaces are the same. You just need to be aware of some small things such as like objects, ensure that they're GPU objects, and ensuring that before you're going to use it, you want to upload these frames into GPU memory. So OpenCV license is based on the BSD license. It's very easy for commercial and research use. So this license allows you to use OpenCV, but it does not require your project to be open source. So it's not necessary to contribute back, but we would always like to encourage you to do so. So next I'll be covering another open source project that is called Point Cloud Library, also known as PCL. So 3D point clouds, this is basically a set of vertices in a 3D coordinate system. Typically, you generate these points through a 3D scanning process. It's used in a variety of applications like CAD, manufacturing, medical imaging, computer vision, and now with like the Microsoft Kinect camera, we see that used in games. 3D point clouds typically have large amounts of data, and it needs to be processed within a short time constraint. So by having a real-time requirement for this means that you need to have very fast computational resources. Typically, when you capture something with point clouds, there's a lot of data present, and GPUs have the compute power and the bandwidth available for providing interactive frame rates at high resolution. And also, the nature of point clouds is inherently parallelizable. So a lot of these operations performed on these 3D points are done. They're pretty much doing the same type of operations for a particular frame. So this this Microsoft Kinect camera is basically when this became available, there was a lot of excitement in the computer vision field for research, because here you have a camera that is less than $200 and is able to capture like 3D point clouds very easy. And so how it works is there are two cameras on the Kinect camera, and there's a IR emitter. And what it does is this camera projects an IR pattern that is basically projected out into the environment. And then you have two cameras. You have one camera that is a color sensor and one that is an IR sensor. And what what this camera does is it reads in this structured pattern. It's kind of like it's a special, it may look like a stochastic pattern. And then basically compares it against a reference image, reference pattern. So by looking at the differences between these two patterns, you can basically infer, okay, what the depth of this, of what you're scanning may look like. And you can generate this, interactively. So, as I mentioned, this is an open source project. It supports a number of OS platforms, and we've also been working on, adding support for Android with this. So PCL has CUDA support enabling GPUs, and we also have recently enabled a lot of this development with Tegra 2 and Tegra 3 platforms. So the project started in March of 2011. So Microsoft had this also developed this this little application that's called Kinect Fusion, and it was very interesting. We'll show you a little demo of it at the end. But basically, the PCL developers were also interested in developing this. So there's an open source version of Kinect Fusion that's developed on their own. So this year, NVIDIA and also PCL, as well as Google, were actually working together to basically contribute to the point cloud projects. So the point cloud library offers a number of algorithms that you can use. You can have filtering, like feature estimation, surface reconstruction, registration, model fitting, and segmentation. So if we were to look at a little demo of what the video is, so this is basically taking image acquired from the like a Microsoft Kinect camera, and here you see on the left is the color. This is the color image, and then on the right you see the point cloud being reconstructed, and then on the bottom here is actually like a depth map that is computed from this information from the camera. So when you acquire this point cloud information, this data can be somewhat noisy. So it's important to basically filter this data, and we can do so with point classification, elevation, intensity, and location within the map. And because filtering serves a good purpose to basically reduce the amount of noise and improve the accuracy for acquiring these point clouds. Now, once you have these point clouds, you can basically do some things like surface reconstruction, and basically it involves generating a 3D mesh from point clouds. With these meshes, you can start to visualize, and build objects within the scene, and also. You can apply texture maps. So if you also capture the color information, you can apply that on top of the 3D mesh. So you can start to visualize, different aspects of a scene, and with this surface reconstruction, you can also later start to determine, okay, what is a floor, what is an object, and anything that may be obstructing the scene. So we can see behind the milk carton there's a little shadow which indicates that. It's basically blocking the scanning. So if we were actually going through, we can move the scanner behind it. So basically, we'll start collecting the 3D point clouds from behind a particular scene. So segmentation here is used for segmenting point clouds into distinct sectors. What we're doing here is we're using it to, try to reconstruct the scenes from point clouds. So we can extract, maybe you have a table with some various number of objects on there. We want to know what exactly these objects are. So by segmenting them, we can basically process each one of these segments separately. And based on that, we can determine, okay, we can try to identify what these objects are. To get started with PCL, you just need to go to this website here. You can download the pre-built binaries or the source code there. And much like OpenCV, basically to use a lot of these CUDA functions, you just need to specify the proper class. And the interfaces, they define them to be the same type of interfaces as the CPU with some minor differences. And the last library I'll cover is the NVIDIA Performance Primitive Libraries. So this is basically a collection of GPU-accelerated image, video, and signal processing functions. This is implemented entirely in CUDA, and in most functions we average about 5 to 10x compared to the optimized CPU versions. With CUDA 4.2 Toolkit, we have about 2,000 image processing functions and more than 600 signal processing functions available. So it provides a set of low-level primitives for arithmetic, logical ops, filtering functions like you can think of box filter, color space conversions for handling YUV to RGB conversions, algorithms such as DCT used for JPEG. It even has some high-level functions such as graph cuts. And with the latest version of NPP, we support 4 to 8 neighborhoods. Basically, having more neighborhoods allows us to basically do better image segmentation within the scene. So you can see, this is an example of a graph that's running. You can take a particular image, you can basically apply bounding box, and graph cuts will basically go through and remove the background from an image. Generally, we find that graph cuts runs about 4 to 5 times faster compared to optimized CPU versions. So what's required is basically the CUDA Toolkit. So you can download this from the NVIDIA developer site, and you need a GPU with CUDA capabilities. With NPP, with the CUDA Toolkit, we included a number of these samples just to show you how to use NPP. GrabCut is this demo that you see down here, which has the turtle and you're extracting the image. So it's something that you can run interactively. So I'd like to also point out a few related talks on computer vision. So 2 o'clock today, there is a talk about the point cloud library from the I believe it's from Radu's group. And 4 o'clock, we have a talk on basically detecting and tracking of NVIDIA glasses with 3D vision. So using many of these computer vision libraries and also our own algorithms that we developed, we basically were able to develop a method for detecting and tracking glasses that people are wearing. And then tomorrow, there's a talk with regards to graph cuts, basically image and video background removal using CUDA. So last, we have a quick demo here. Basically, we're going to show you the Kinect Fusion demonstration here. James is going to do the demonstration here.